Not do me. Okay, I can write all the way to here. I can even go further because I think I can do that. Other way. Okay. Ugh. Ugh. Today is August 26th. We got a little bit to clean up from section 1.2. We were talking about triangles that were similar, and I think we ended there without having any discussion of what that meant and how we could use it. So let me give you an example here. Objects are either similar or congruent. Congruent means the exact same size and shape. Similar just means proportional size. So, so back in section 1.2, similar triangles are those whose angles are pairwise congruent. All right. Angles are pairwise congruent, right? That's the end of where I can write right there. In other words, if I have a triangle over here, and I know maybe that this is a 30-degree angle, and this is probably maybe in the neighborhood of a 40-degree angle. Can anybody tell me the measure of this third angle? 110, because everybody knows that the sum of the angles in a triangle is 180 degrees. So these add to 70, this means this has to be 110 degrees. If I have another triangle that has those angle measurements, that's what I mean by pairwise congruent. And I don't even have to know those. If I just know two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. And similar triangles have the property that the sides are proportional. That if I knew the lengths of the sides here and whatever scale factor, I could get the lengths of the sides there. Just like if you go to a shoe store and pick out a style of shoe you want, you tell them your size. And if somebody with you wants the same shoe but in a different size, they'll get the same shoe but a different size. They're proportional. When I say triangles are similar, that means their sides, oops, I said I couldn't write over there, are proportional. So let me scoot this bad boy a bit. There we go. Sides are proportional. Still looking up a little bit. Let me get that. What did I read in? Pressed my luck, didn't I? Okay. That says that, for instance, suppose I know that this triangle has sides, I don't know, let's say that this is 10 units long. That might be 15 units long, and just making up numbers, this might be 70 units long. And then maybe by chance I tell you that this is 30 units long, and I want you to find that length and that length. Pick nice, easy numbers. What do you think the lengths of A and B would be? Since this corresponds to this side and it's 3 times larger, all of the other sides that correspond are 3 times larger. So 3 times 15 And then here's 3 times 70. Now, if that number isn't obvious to you, it could also be a fraction or a decimal. So what you would do in order to find those is you could say something of the order that 30 is to 10, the side included by those 2 angles in the corresponding part, is to A over 15 is to B over 70. So if the number doesn't jump out, you set up the proportions. And then you can just grab a pair of them and solve. 30 over 10 simplifies to 3. And then multiply both sides by 15. And then you could do the same thing here. I picked one that we can eyeball so that it made sense to me. Okay? So we're going to use that when we develop our 6 trig functions. We can also use something like this, like I think one of your web work problems says you want to find out how tall something is, maybe a flagpole, right? So web work has something like, here's a flagpole here. And you want to know how tall it is. And you don't want to climb up there with your tape measure, but you do have a tape measure, and you can see that when the sun is at a certain time of day, it's dropping a shadow down here a certain length. So let's say the length of the shadow at that time of day is 12 feet. Well, now what you know is that you're, I don't know, this will be me, and I'm 6 feet tall. I look shorter in person. And then when the sun drops the shadow on me, it looks like my shadow's about, I don't know, 4.5 feet. I know my height, I can easily measure my shadow. I can measure the shadow of the light pole or the flagpole, and now I can figure out how tall the flagpole is. Because these make similar triangles. The angle that's similar is this one here and here. Those 2 are the same. And this is in Lubbock, so this makes a perfect right angle with the ground. So I've got 2 angles that are congruent, so the parts are now proportional. So the height of the flag is to the height of the person, as the shadow of the flag is to the shadow of the person. So all I've got to do is solve for h. And that would be in units of feet. Let me show off my arithmetic skills. 6 times 12 is 72. 4.5 is a fraction, 4.5. 4.5 is the same as 9/2. To divide a whole number by a fraction, you flip the fraction over here and multiply. 9 times 8 is 72. 2 times 8 is 16. That's a 16-foot tall flagpole. I got lucky. I got lucky to have nice numbers. If there was a 17 in there, I'd be like, fine. Okay? You've done stuff like that, right? Maybe in 5th grade or something. Okay, so here's how we're going to use this. There are 2 sections left in chapter 1, 1.3 and 1.4, and I'm going to kind of bleed them together. We introduced the 6 trig functions and their properties and relationships. Okay, ready? Yeah, now I get to erase with my little black towel. So put sections 1.3 and 1.4 together. I've got another web work that just opened up covering those sections. We're going to look at our 6 trig functions. And we're going to today define the trig functions based upon coordinates in the XY plane. But we're going to extend that later on in the next chapter. So if you take an angle in standard position, which means it has its vertex in the origin, and you rotate that around the XY plane, an angle is formed with the positive x-axis. So suppose I rotate the ray to about right here. And the angle's formed with the positive x-axis. Further, suppose that this ray passes through a point that I know. I know the ordered pairs of a point that it passes through. Suppose it passes through the ordered pair xy. Then I can drop down this perpendicular segment here and make a right triangle whose base is x units long and whose height is y units long. And let's call this length from this point to this one r units long. I made a right triangle, so if I know the exact values of x and y, I can find r as a number. How would I do that? The Pythagorean theorem, which says that in any right triangle, leg squared plus leg squared is hypotenuse squared. So that number r will always be known. We define 6 trig functions as functions of the size of this angle. They're going to be the sine, cosine, tangent, secant, cosecant, and cotangent, all as functions of that angle. So the 6 trig functions written out we've got a sine, cosine, tangent, cosecant, secant, and cotangent. That's the way you write them, but they're functions of an input variable. They take an input, theta, and produce a numerical output according to the following definitions. We abbreviate the sine as sin, and then its input value is theta, and it's defined as the ratio between the height of this perpendicular segment divided by the number r. Y, I said. The cosine of that angle theta is defined as the width of the base, x, divided by r. The tangent of that angle is the slope of that line segment. Can anybody tell me the slope of the line segment from 0, 0 to xy? Y over x, rise over run. Rise over the run. The cosecant is abbreviated CSC of that angle theta, and it's the reciprocal of the sine values. It's r over y. Or you can always think of it as 1 over the sine. The secant is the reciprocal of the cosine. We abbreviate secant as SEC. And it's going to be r over x, or 1 over the cosine. The cotangent of angle theta is abbreviated COT, and it's the reciprocal of the slope, x over y. When I write them like this, cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent. Those are called the reciprocal identities. All right, so let me get you guys to plot a point in the XY plane. Plot the ordered pair. X is 12, Y is 5. And draw a line segment from that point to the origin and find out how long that line segment is. O is the origin, and then theta is the angle from ray OP to the x-axis, or vice versa, doesn't matter which way it goes. Find sine theta, cosine of theta. I'm not going to use the parentheses anymore. I put them there so that you can see the function relationship, that's the input value, and then this is the output value. So I'm going to not write them anymore, because then I have to erase them. Tangent of theta, the cosecant of theta, the secant of theta, the cotangent. How much we can see, or do I need to flick my camera? I do need to flick the old camera. Okay. So the point 12, 5 means x is 12, y is 5. So that should be a point in the first quadrant. So x is 12, y is 5 to about right here. There's the origin. We're going to construct this ray here. I'm going to drop this perpendicular down here. And here's the angle that we're talking about right there. So I've given it no direction. I'll imagine a ray going that way maybe. So that means in our picture, the width of the base is 12 and the height of that triangle is 5. Use the Pythagorean theorem and see if you can tell me what R is. 13? Are you familiar with some Pythagorean triples? Some nice whole numbers that satisfy the Pythagorean identity. One of them is 3, 4, 5. Another one is 5, 12, 13. 5 squared plus 12 squared is 13 squared. There's another one that has a 17 in it, but those are the only two I remember. But we find that 13 because R squared is 12 squared plus 5 squared. That's 144 plus 25. Goes out to 169. And so R is the square root of 169. And if you don't believe me, try it out on a calculator. That is indeed 13. Now we have the picture. We've got the X, Y, and R. Now we just look over there and set up the ratios the way we're supposed to. Sine is Y over R. So in our picture, sine is 5 over 13. Cosine is X over R. Our X is 12. R is 13. So cosine is 12 over 13. Tangent is the slope or the rise over the run, y divided by the x. So that's 5 over 12. I wrote them in this order so that they match the reciprocal of those written in that order. The cosecant is 1 over the sine. So flip that number upside down and you get 13 over 5. The secant is 1 over the cosine. So you get 13 over 12. And the cotangent is 1 over the tangent, which is 12 over 5. So let me just remind everybody that this was y over r. This one was x over r. This one was y over x. This one is r over y. This one is r over x. And this one is x over y. Not too far over that way. The picture didn't quite make it. So it's not hard, just a little tiny bit of memorizing. Very little, right? Okay. Now what we're going to do is take a line and pass it through the origin and then form an angle. So let me try to use the same example that I used this morning so my Zoom can apply to those kids as well. Okay, so let's take the line 3x minus 2y is equal to 0. Draw me that line, 3x minus 2y is equal to 0. And then consider that portion of the line where x is negative, and draw the perpendicular from that portion of the line back up to the nearest x-axis.
Could you rephrase that? That I couldn't really, I found that a little confusing.
All right, I'm gonna write it, maybe it'll make it better. Graph the line. 3x minus 2y is equal to 0. And then for x less than or equal to 0, consider the angle theta formed with the x-axis. Find the values of the 6 trig functions. Of this angle. So when I'm doing this stuff, just to keep you from having to write real fast, I do that a lot. I'll say the problem, and then I'll write the problem, and then I'll probably say the problem, so that it keeps me from writing too fast after I've spent all day thinking about it. So I want to know, do you know how to graph a line? And would you, and how can you know if this line goes through the origin? It doesn't have a y-intercept other than 0 here, right? Or the ordered pair, x is 0, y is 0, when substituted in here, makes a true statement. Okay, if I had another number over here, it would not pass through the origin. That picks the graph up or down. All right, so you know 0, 0 is 1 point on this line. I want you to find another point on this line. Find another ordered pair that satisfies this equation. There are infinitely many, and it doesn't matter which one you use, because I'm going to show you we generate similar triangles. So just for fun, that's what we're all about here, find me at least 2 more points that satisfy this equation while I erase the board. No, that one satisfies the equation. Does anybody have an ordered pair?
2, 3, and 4, 6.
Okay, when x is 2, then we get a 6 right here. And if I want this to subtract off, then y has to be 3.
4,
So-
6.
2, 3 satisfies that equation. And you said 4, 6?
Yes.
So x is 4, makes that 12. So if I want to subtract off a 12, y would have to be 6. All right, so that line is going to go through these points. Okay, now continue the line because I said I want x to be negative. So for instance, what if x is -2? What is y? -3? Right? -2 makes this a -6. And if I want to subtract off a -6, I need a -3 here. And I would bet, what was this point here, 4, 6? I bet -4, -6 is also on this line. So I said, consider the angle formed with the x-axis for these. So I'm defining theta as this angle right here. So we can see better. I'm going to go ahead and make my perpendicular here. But look, it doesn't matter which point I use, because if I use this ordered pair, I've got this little brown triangle here and this larger triangle there. They share this angle and they both have a right angle. So that means they're similar. So that says that this is to this as that is to that, right? 2 is to 4 as 3 is to 6. They both simplify to the same ratio, right? So it doesn't matter what point you find. You generate a right triangle somehow by finding a point in the described region and draw up a right triangle. So now I'm going to look at not this little baby poo color. I'm going to use this triangle here. This side then has as its coordinate -4. This has a coordinate of -6. So now we need to find the length of the hypotenuse. We need to find R. Not going to get a nice whole number this time. I don't want any decimals. Let's keep things in radical form.
Well, 2 and 3 was square root of 13.
Okay. 2 and 3 gives you the square root of 13. This will give us, I think, 4 square root of 13 or 2 square root of 13. Let's find out. Okay. So let's see, I've got x squared plus y squared is r squared. X is -4, y is -6. So I get 16 plus 36. Is that 52? And 52 is r squared. So r is the square root of 52. But you happen to notice that 52 is the same as 4 times 13. And the square root of 4 is a perfect square. So I can write the square root of 52 as 2 times the square root of 13. Now we can get our 6 trig functions. Yes, sir.
So in terms of finding numbers like that that can be split off into like 2 root 13, for
Uh-huh.
instance. Say if that's something we find on a test, doesn't matter if we have it either or.
Yeah, I don't, if you left it as the square root of 52, I'm perfectly happy.
Great.
I was again showing off my mathematical skills. I want you to know that you're in the hands of a trained professional until I get to this part. There are some days I just can't do numbers. But today I'm okay because I did these same numbers this morning. So I had practice. Okay. Let's find the sine, cosine, tangent, cosecant, secant, cotangent of that angle theta using our definitions of x, y, and r for those trig functions. Okay, so find the values of the 6 trig functions. The sine of theta, cosine of theta. Now I'm getting the wet part. Nope, that's not going to work. Let me let the board dry a bit. Okay, come on now. Tangent of theta. So sine is y divided by r, cosine is x divided by r, tangent is y divided by x. If it's easier for you to learn them in the other order where the cosine is written first, that's a you thing, because I learned them this order, I always do it in this order. Okay, so the y is -6 and the r is 2 square root of 13. R is always positive.
Oh, okay.
R is always positive because of this step. I square and then I take the square root. Okay, we're always going to get R as a positive number. X and Y are according to the coordinates that we're using, but R is always, always positive. Okay, and if you want, the 2 divides into the -6 and leaves you -3 over the square root of 13. And then tell me how I get from that to this. Do you recognize that those two are the same numbers? -3 over square root of 13 is the same as -3 square root of 13 over 13. Remember that? Remember when you were in algebra or something and you were always forced to rationalize the denominator? You multiply top and bottom of this by the square root of 13. The square root of 13 times the square root of 13 is the square root of 13 squared, which is just 13. So this is rationalizing the denominator. That's not something I'll make you do, maybe, but I think that sometimes is asked for on web work. All right. Cosine is x over r. The x in our picture is -4. So I have -4 divided by 2 square root of 13. The 2's again cancel. So I get -2 over the square root of 13. And if you multiply top and bottom by square root of 13, then the denominator does not have the radical that the numerator does. Tangent is y over x. So the y value is the -6. The x is -4. The negatives will cancel. 6 over 4 is the same as 3/2. Yes.
So do you want us to simplify when we put it into those trigonometry equations?
I don't care. It's just if the web work directions ask you to, then you gotta listen to web work.
Okay.
But you could leave it here. But the moral of the story is work with radicals. Don't give me decimals here. Okay, don't waste your time pulling out a calculator and giving me decimals because we're not going to use calculators on the test. Okay. All right, now let's go and flip these over. What was the reciprocal of the sine called? Cosecant. So the cosecant of this angle flips this guy over. Let's just flip it over from before we rationalized it. The cosecant is square root of 13 over -3. It doesn't matter if I leave the negative with the 3 or if I type the minus in first and put the ratio over here. That's the same fraction whether I have the minus here or on top or in front. The reciprocal of the cosine was the secant. So let's take it from this form and flip it over. So we write square root of 13 over -2. But I think it looks better with the minus sign out front. The cotangent is the reciprocal of the tangent. And that's going to be 2 over 3. Okay. Any questions? Okay, now let's find the values of our 6 trig functions for angles that are coterminal with our axes, with the positive x-axis, with the positive y-axis, with the negative x-axis, and with the negative y-axis. So let me see how far over here I can draw. So my next example, we're going to find the values of the 6 trig functions of the quadrantal of the quadrant QUADRANTAL. So angles that correspond to the lines that break up the 4 quadrants. And so I'm going to ask you what those angles are. I'm going to spot you the first one. If the ray is coterminal with the positive x-axis, that ray has rotated 0 degrees. So what if the ray rotates up to this axis right here? That's a 90-degree angle. That's this one. What angle is made with the straight line? Good. And then all the way around to here, 270. They're all 90 degrees apart. And then whatever is 0 degrees is the same as 360 and so on, right? So I want to find the values of the sine of 0 degrees, cosine of 0 degrees, tangent of 0 degrees, blah, 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 blah. Then we do it again here, here, and here. So I'm going to put it in a table, and that way I don't have to do it separately. Question? Basically, that part of it. Let me make a big old table here. Yes, sir.
What does a coterminal mean again?
Lands there. It lands on that line.
Okay.
Right, lands after moving. We make an angle by rotating. So this arm now is coterminal with 0 degrees.
Okay.
By rotating here, it's coterminal with 90 degrees. Can't do that one. Look at here. Okay, so I want 4 columns, actually 5 columns. I need a heading. I've got my angle. Then I've got 0 degrees. These are rows, not columns, right? 90 degrees, 180 degrees, 270 degrees. And I don't need the 360 because it's the same as the 0. Now we want 5 columns. 6 columns. Good gosh, I can't count. I want the sine of that angle theta. Cosine of that angle theta. tangent, cosecant, secant, and then finally the cotangent. So to remind you, the sine is y divided by r, cosine is x over r, tangent is y over x. So the cosecant is 1 over the sine, secant is 1 over the cosine, cotangent is 1 over the tangent. So an angle of measure 0 degrees lies on the x-axis. Can you give me the coordinates of any one point on the x-axis, for instance? 2, 0. 2, 0 is on the x-axis. So I've gone over 2 units, that's the x, 0 units on the y. Now r is the square root of x squared plus y squared. So for this ordered pair, 2 squared plus 0 squared brings us all the way back to 2. So x is 2, y is 0, r is 2. Use those numbers and tell me what is the sine of 0 degrees. Y divided by x. I'm sorry, y divided by r. 0 divided by 2. That is 0. Cosine of 0 degrees is x divided by r. X is 2, r is 2. Cosine of 0 degrees is indeed 1. The tangent is the y divided by the x. Take the y divided by the x, you get 0 divided by 2, you get 0. Cosecant is the reciprocal of the sine. But, the sine is 0. What do I say for my value of 1 divided by 0? Yeah, doesn't exist, it's undefined. So your book says undefined. So that's what I'll write, because it gives me 0 in the denominator. Cosine is 1, so the secant is 1 over 1. That means the secant of 0 degrees is 1. What are you going to say about the cotangent of 0 degrees? That one is also undefined. Okay. Next, 90 degrees, an example of a point on the y-axis.
0, 3.
I'm gonna go with 1.
All right.
Because I put it closer to 1 than I did to 3. If that's 2, then that looks like a 1. X squared plus y squared is r squared. For this 90-degree angle, what is r? R is also 1. X squared plus y squared adds to 1. Square root of 1 is 1. So x is 0, y is 1, r is 1. What then is the sine of 90 degrees? 1 over 1 is 1. What is the cosine of 90 degrees? Cosine of 90 degrees is x over r, 0 divided by 1. The tangent of 90 degrees is y divided by x. So 1 divided by 0 in this example. 1 divided by 0 is undefined. Now start flipping them over. The cosecant of 90 degrees will be 1 over 1. So 1 over 1. The secant of 90 degrees is 1 over 0. So it's undefined. The cotangent is 1 over the tangent, but maybe we better look at that as x over y. Over here, the x over the y simplifies to 0, or simplifies from 0 over 1 to 0. Okay? Okay. Back here, I don't know. Let's use the point -2, 0. And if x is -2 and y is 0, do you agree that r is also 2? R is always positive. -2 squared is 4, plus 0 is 4, square root of 4 is 2. Okay. So the sine of 180 degrees is y over r. So it'll be 0. The cosine of 180 degrees is x over r. So I would have -2 over 2. The tangent is y divided by x. So 0 divided by -2 is 0. The cosecant is 1 over the sine. But look, the sine at 180 degrees is 0. 1 over 0 is undefined. Here's pattern. The secant is 1 over the cosine. 1 over -1 is still -1. The cotangent is x over y. Y is 0, so x over y is undefined. So if I just project this point back down here, point on this line is 0, -1, which makes r equal to 1. So when I talk about the sine of 270 degrees, I take -1 and I divide it by 1, and I get -1. The cosine of 270 degrees is y over r, x over r, 0 over 1. The tangent is y over x. So -1 divided by 0 is undefined. Cosecant is the reciprocal of the sine. So if I flip over a -1, I still have a -1. 1 over cosine, flip over a 0, that's not defined. And then x over y, x is 0, y is -1, 0 over -1 is 0. So the picture tells us the values. But now we can use that to find things like what is the sine of 450 degrees?
Oh,
Yes, sir.
the sine of 450 degrees is 0.
Okay, can you tell me how you did that?
Because if you just do a full circle, that's 360, and you add 40 more to make it 400, plus another 50, which just brings it back to that.
Good. 450, if I start removing laps around the circle,
Oh, one, sorry, my bad.
is 1 lap in the circle. So this 450 degree angle is coterminal with the 90-degree angle. In other words, I form this angle by taking a full lap and a quarter lap, and that is a 450-degree angle. So the value of the sine of that angle is exactly the same as the value of the sine at 90 degrees, because it's coterminal with that ray. So that's the sine of 90 degrees. The sine of 90 degrees is 1. Next one. How about the tangent of 1800 degrees? The hint is that this is one of our quadrantal angles that are over there. So start taking out 360s from this. And when you get a number between 0 and 360, you should recognize it from one in the table.
0.
0? Because 1800 is the same as 5 times 360. Or you just subtract 360 until you run out of 360s. Right? That means that's the same as the tangent of 0 degrees. What is the tangent of 0 degrees? Well, 0, if you don't look at the table, 0 corresponds to the positive x-axis. Tangent is y over r. On the positive x-axis, every y is 0. So y over x, 0 over any x is 0. One more. How about the cosine of a negative something something? How about a negative 900? Negative 900 degrees. So this time you're going backwards. So it says subtracting 360s, add some 360s until you recognize an angle. Okay, so negative 900 plus 720, which is 2 360s, gives you a negative 180. So if you go that way around the circle, that's negative 90, negative 180 is coterminal with 180. Agree? So you'll get the same kind of ratios here. So cosine is x over r. So negative 2 over 2, negative 1. Okay? Now we don't know any of the other ones just yet, but we can predict the sign, S-I-G-N, of the other ones if we know what quadrant an angle will have its terminal side in. So I want you to decide DEC, if following is positive or negative. So how about the sine of 310 degrees? So really what I want you to tell me is in what quadrant the terminal side of a 310 degree angle is. You agree it's in quadrant 4? Because all the way around is 360. 2/3 of the way around is 270. So that's a number in here. That puts it in quadrant 4. The sign is related to the y value. In quadrant 4, are the y values positive numbers or negative numbers? They're all negative. R is always going to be positive, but in quadrant 4, all the y values down here are negative. So we'll have a negative over r, which makes this a negative. Okay? All right. So we can make a drinking game out of this. You miss, you got to take a shot of chocolate milk. Root beer. Cosine of about I guess I'm making them up. Negative 250 degrees. They want to tell me what quadrant an angle of measure negative 250 would be? Which one? Or negative though. You're right, it is 2. It is 2. So negative 90, negative 180, negative 270. So negative 210 is going to be quadrant 2. In quadrant 2, cosine is related to the x's. So if you're going to plot a point in quadrant 2, what is the sign of the x? It is a negative. So you don't have to take a shot of your chocolate milk, do you?
Next time.
How about the tangent of 1,234 degrees? Positive angle. I'm going around a few times. Does anybody know how many times I'm going around? 1800 was 5 times. So it's 4 times 360.
It's in quadrant 3, right?
So that's 1440. So it's not 4 times around. So 3 times 360
Yeah.
is 1080. So let's take 1080 out of that. Let's go terminal with an angle of measure, 154 degrees. 154 degrees is in quadrant 2, not quite 180. So this is a quadrant 2 angle. In quadrant 2, x is negative, y is positive, tangent is y over x. So I said y is positive, x is negative, so it's going to be negative.
Doesn't, as long as there's a negative in that quadrant, it's always going to be negative, right?
Correct.
Yes.
Right. So you make it a positive no matter what you do.
Wasn't that fun?
Yeah.
It's a lot more funny when it's a real drinking game, because after a few losses, you're just. That chocolate milk will hit you hard.
That's so much fun.
All students take calculus. That's how I remember the signs of my trig functions. All students take calculus. All 6 of our trig functions are positive in quadrant 1, because in quadrant 1, x, y, and r are all positive. Okay, all the trig functions are positive here. Only 2 trig functions are positive in quadrant 2, and those are the ones that have the y coordinate positive. The ones that depend on y are the sine and its reciprocal. What's the reciprocal of the sine called? So the sine and 1 over the sine are positive here. The other 4 trig functions are negative here, because they depend on x, and x is negative here. R is always positive, so they follow the sign of either the x or the y. Y is positive here, so the sine and 1 over the sine is positive here. The T for take stands for tangent. Only the tangent and its reciprocal are positive in quadrant 3, because in quadrant 3, both x and y are negative. And a negative divided by a negative makes a positive. The other ones have the r in them, and r is always positive. So only tangent and 1 over tangent are positive here. That leaves us cosine and 1 over the cosine. Cosine depends on x. In quadrant 4, the x is positive, the y is negative. So x over r and r over x, which is cosine or the secant, are positive here. Okay, so all are positive. Sine and 1 over the sine are positive. Tangent and 1 over the tangent, positive. The cosine, 1 over the cosine are positive. The other ones are negative. So then you don't even have to work that hard. All students take care. Unless you say it fast afterwards. Okay, now another thing is when we're finding these x's and y's and r's, we're making right triangles. In a right triangle, is it not true that the hypotenuse is always the longest length? And then that makes the ratios, or that makes x and y always smaller than r, unless of course they're equal to r when they're quadrantial. So if you make the ratios of x to r or y to r, is that fraction going to be a number bigger than 1, smaller than 1, or at very most equal to 1? If r is the bigger of the number, that's going to be smaller than 1. It's possibly equal to 1 if the angle is in the quadrant. If x is negative, r is positive, what's the very smallest value x over r could take on? Could it be a number like negative 3.2? Not if r is bigger, right? R is always bigger than x, even if x is negative. So if r is bigger than x, this can never be any smaller than negative 1, which means the cosine as a value will never be bigger than or smaller than negative 1. So I guess I get to erase. That's the part that I love. No matter what the angle, sine and cosine will always take on a value between 1 and negative 1. Now, as we plot points in the plane, sometimes y is bigger than x. So y divided by x can be bigger than 1, right? Sometimes x is 0. So y divided by x can get infinitely large. That means the tangent can take on any value in the world, positive numbers and negative numbers. So the tangent can be any size number. Now, if sine is between negative 1 and 1, its reciprocal, sine can take on a value, for instance, like a third, right? That's a number between 1 and negative 1. So its reciprocal, which would be the cosecant, would be a number like 3. But sine can be even 0, and 1 over 0 is not defined. Right, so the cosecant sometimes can get infinitely large. It can be a number like 3. Sine at its very biggest is 1. 1 over 1 is 1. So I'm thinking, see if you're thinking along with me, that 1 over the sine is always 1 or more. Unless it's negative, then it's negative 1 or less. So the cosecant of an angle in absolute value is greater than or equal to 1, which means the cosecant of an angle is either less than or equal to -1 or greater than +1. So that's a quick way of saying that. The cosecant is never going to be able to spit out a value like a half because there's no value here of 2, right? Same deal here. 1 over the cosine can never spit out a value of a half. The range of the secant function follows that. The secant of theta is always an absolute value bigger than 1, which again means the secant of theta is either less than or equal to -1, or the secant of theta is greater than or equal to +1. The tangent can be any size number. It could be a whole number. I can find an angle for which I take the tangent of to get a number like 50. So the cotangent can be something as small as 1 over 50. But the tangent itself can be 0. So the cotangent can also become infinitely large. So the range of the cotangent function is also in here. So another game you can play is possible or impossible. All right, don't look at this. Just use your logic. We'll play possible or impossible. Is there an angle theta that I take the sine of to get -3?
Impossible.
Impossible, because sine is bounded by 1 and -1. What about secant of theta? Can I get it to equal -3?
Yes.
I would just have to take 1 over -1/3. Cosine can be a -1/3. And so, yes, that's possible. See, this one's not as fun. Not as fun as quadrant. Quadrants give you have more choices. So what else I got to tell you? Okay, so you said the Pythagorean identity says that in any right triangle, x squared, which is the horizontal leg, plus y squared is equal to the hypotenuse squared. I'm going to make them plural. I'm going to show you 3 more versions of the Pythagorean identity. 3 more than this. In any equation, I can divide both sides of the equation by any non-zero number. So I'm going to divide both sides of this equation by r squared. And I'm going to think of x squared over r squared as x over r all squared. Y squared over r squared will be y over r all squared. And this, of course, is just 1. Which trig function is x over r? Cosine. So I can say the cosine of an angle theta squared plus, what's this one? The sine of an angle theta squared is 1. Make sure you include the angle. Without the angle, COS by itself is not a function. So it's the cosine of theta squared plus the sine of theta squared. And maybe you've noticed that in math, we try to lessen our use of parentheses at every opportunity. So we write this cosine of an angle squared like this. We put the square next to the function and then the angle. And that means that you're squaring the entire value of the cosine of theta. So that is called a Pythagorean identity. The other two, I do the same kind of trick. I can divide by any non-zero number. So let's assume that x is not 0. I'm going to divide every term by x squared. Then I'm going to do this dilly over here with the parentheses. X squared over x squared is 1. Think of y squared over x squared as y over xr squared, all squared. And then r over x, all squared. Y over x, I erased it. Which trig function was y over x? Tangent. So this has 1 plus the tangent function squared is equal to, which trig function is r over x? Secant. Secant. X was cosine, right? So that's 1 over cosine. So this version says that 1 plus the tangent squared of an angle is equal to the secant squared of an angle. Okay. If I divide by y squared, I get the same deal, except for I'd have an x squared over y squared here, y squared over y squared here, r squared over y squared here, x over y all squared. Which trig function has the x over the y? So cotangent squared, this would be +1, and this would be r squared over y squared. So which trig function is r over y? Cosecant. Cotangent squared +1 is equal to cosecant squared. These are the 3 Pythagorean identities that we refer to in calculus and in trig and in life. Okay. Right. So if I know the value of any one trig function, even if I don't know the angle, if I know the value of any one trig function, I can get all 6 of them. Right? If I know the sine of some mystery angle is 1/3, I put that 1/3 here and I solve for the cosine of that angle. Once I know the cosine of that angle, then I can find an R that makes that true, right? I can plot those points. And then I can get all the rest of them. So I'll do an example of that next time, but that might be enough to send you off into a weekend or something.